different points in time matters. Okay? Any questions about that? Okay, so we haven't really talked about anything chemical. Let's get back to the chemistry. This is too much physics for us. So let's talk about enthalpy changes of chemical reactions. So enthalpy. Chemical reactions. So a lot of times you'll hear probably your high school teacher say enthalpy is the same thing as heat transfer. That isn't quite true. It depends on the conditions of the system that we have. Enthalpy always confused me when I was an undergrad. It wasn't until I started really diving into it that I understood it. So I'm going to try to relay it to you guys so you can understand it better. So you don't have to waste, 4 years of your life studying this junk to figure out what this means. So the idea is we want to look at the heat transfer of a reaction, right? We want to know if our reaction is going to release a lot of heat or not. Let's say we make an MRI contrasting agent that goes through the blood-brain barrier, it goes into people's heads. Do we want to release a lot of heat into somebody's brain? Probably not. You're going to denature a lot of proteins and basically fry them. Do we want a system that's going to absorb a ton of energy? Not really either. So knowing these things can be very beneficial if you're making like pharmaceuticals. If you're considering industrial processes, you don't want the plant to melt down. So we want to figure out what's going to happen with this heat change. We seek to determine the heat transfer of a chemical reaction. Okay, and there are two scenarios. We can have constant pressure or we can have constant volume. So let's ask the first question. Can we do this under constant volume? So if we're talking about heat transfer, we got to jump back to the first law of thermodynamics, where we said delta U. What's delta U going to be equal to? Or what have we said so far, mainly this class? It's equal to what? Yep, Q plus W, right? So we got heat transfer and we have the work done. Now we're going to say, yeah, Olivia?
So how do you know when you're going between, like, how do you know what equation you're like switching back and forth?
It depends on the outcome. I know from experience, I have a certain outcome I'm trying to get to right now. Okay? Most of the time in this course, we're going to be using this. Okay, since we say a constant volume, what we're going to do, we're going to give this Q a sub V. So we can say it's the heat transfer under a constant volume scenario. Now, we have another equation for work. Let's say we assume we have an ideal gas. Meaning we only do pressure volume work. What happens to work? Or how did we define work again? Work was equal to what for a gas? Delta V, right? So then this becomes negative P times delta V is equal to delta U. But what did we say? What are our experimental conditions? What do we have constant? We have constant volume, right? So does that influence this equation right here at all? We have a constant V. What happens to this term? 0, there's no change, right? So this is 0. So let's simplify this equation. What does Q sub V equal in this case? Yep, delta U. So what that tells us is, if we measure the heat transfer, we know the change in the internal energy at constant volume, which is awesome because we know the energy flow of the system. If you know about the energy of the system, you can know a ton about that system. But what, does anybody see a problem with this? What are our conditions again? We have constant volume. How frequently, like in the lab, do we keep a constant volume situation? Have we ever? No, we haven't. So this is awesome, but it's useless essentially. It's not very helpful. Constant volume conditions are not easily obtained. So that doesn't help us out a ton. What about constant pressure? So, question, what about constant pressure? Okay, let's jump back to the first law again. Delta U is equal to what always? Q plus W. Okay, since we're at constant pressure, what we're going to do, we're going to give this Q a little sub P to indicate that we're talking about a constant pressure situation. Next, what we're going to do, we're going to assume we have an ideal gas. So assume an ideal gas. So we're only doing pressure volume work. How does this equation change? Delta U is equal to what? Does anything happen to this guy? Nope, stays as Q sub P. What happens to that work? What happened last time? Right. Okay, and the goal was, we wanted to look at the heat transfer. We wanted to find the heat transfer. So let's manipulate this around. Q sub P, what's Q sub P going to be equal to in this case? Yep, so we've got delta U. What else? Well, we're moving this over there, right? So what is it? Yep, plus P delta V. So we can find a heat transfer. This Q sub P is another state function. It's known as enthalpy. Does anybody know what symbol enthalpy is given? Yep, capital H. So the enthalpy is equal to the internal energy plus this pressure volume term. And that's also equal to the heat transfer. So if we measure the heat transfer, we get something called enthalpy. And what enthalpy is it's the internal energy plus this pressure volume term. So it's really related to the internal energy. It's a tiny bit different, but that's what it is. And it took me a while to understand that why are we measuring enthalpies? Why aren't we measuring just internal energies? Well, we can't. Because if we have a constant pressure system like we assume we have in labs, what we're actually measuring is enthalpy, not internal energy. So what we do in the lab, we set up, so enthalpy, delta H, is often used because we assume we have constant pressure in the lab.